Hello and welcome to lesson 6 in unit 3, and we're talking about power and efficiency today, and they're really two different topics here. So the first half of the note is going to talk about power, then we'll talk about efficiency. So I want you to be able to explain both the concepts of power and efficiency and be able to do the appropriate calculations. And you'll find after doing conservation of energy, the calculations are quite a bit simpler in this case. So here's the big thing here. Power is often confused with work, but here's the major difference, and we talked about this earlier in the unit. Work is the amount of energy transferred during an interaction, okay? So when you're pushing a car, pulling a wagon, how much energy are you transferring? Power is how fast you do it, okay? Power is how fast are you working? So using the definition of power, this is what the formula is. So capital P equals work divided by time. All right. Now the formula can look a little bit different. This is where I want to make sure I explain this well. Or power could look like this. It could be force times displacement over time. Okay, and remember, work is just force times distance. Or any calculation of energy. All right. It could be mgh over delta T. So mgh is gravitational potential energy. That's also a possibility. Or it could be kinetic energy. Power is 1/2 mv squared over delta T. So you can substitute any formula we have for energy into the numerator here to do this calculation. All right? So if the question is talking about kinetic energy, that's okay. You can plug it into the power formula. So I have an example for you here. If a 100 kilogram person, oops, let's move this up a little bit. If a 100 kilogram person was to run up the stairs that had resulted in a vertical displacement of 20 meters, so that means that you ran up steps and it lifted you 20 meters above the ground, how much energy was used to climb the stairs? So here's my example right here. To move someone up the stairs, so they went upstairs, and it was 20 meters high. What's gravitational potential? To go upstairs, you're overcoming gravitational potential. So mgh, mass was 100 kilogram, which is about 220 pound person. 9.81 times 20 equals 19,620 joules of energy. Okay. B part. How much power was generated? If it took 5 minutes to climb the steps. Now, here's the key here, and let's just go up here for a second with power. We're going to add in 2 comments here. Power is measured in watts. Oops, measured in watts, or capital W. And secondly, time has to be in seconds. All right, we need to make sure we convert to seconds. All right, so there's your catches if you're looking for what makes this hard. So B part, and we'll do I. What am I doing there? I think it's a vector. I. Okay, so power equals work over delta T. Well, we've calculated the work. Okay, again, this work here is the work there, the gravitational potential energy. So 19,000, now I came in right, 19,620 divided by 5 minutes times 60 on the bottom. And that will get you to seconds. All right, so doing a quick calculation, 19,620 divided by 5 times 60, bracket, gives us 65.4 watts. So this person, if they do it in 5 minutes, they had 65 watts of power. Now what happens if they lollygagged a little bit and did it in 10 minutes? So power is W, delta T, 19,620, 10 times 60 this time on the bottom, because it's 10 minutes. All right, so divide that by 2, and we get 32.7 watts. All right, so someone that takes twice as long is half as powerful. So therefore, if it takes twice as long, it is half as powerful. All right. Okay, so the faster you do something, it means you have more power. The slower you do it, even though you get the job done, it means you have less power. The last one, if you took the elevator instead of the steps, discuss how energy and power must be considered in design. So when you're designing an elevator, the key with the elevator here is the power on that motor to lift it. So we have the car, and we have the cable that goes up, and then we have our motor. All right. So if we want to go up fast, we need a big motor. Okay? Has to be a really big motor if you want to go up fast. All right? It's all about the speed in terms of the motor. A motor is in horsepower. Most of you will be more comfortable knowing how many horsepower, but the equivalent is in kilowatts, which is the metric. It's the equivalent to horsepower, which is imperial. The faster you want to do something, more horsepower you need. So you can use a smaller engine. So you can use a smaller motor, but it will require a slower lift time. All right, so if you go half the power, which we just talked about up here, all right, if you go with a 50 kilowatt motor instead of a 100 kilowatt motor, it's going to take you twice as long for that motor to lift the cart. So when you're looking at it, that motor, you're deciding on talking about size of the motor, how big is the motor going to be, you know, how much room, how much mass do we want up there, and so on and so forth. So when you are doing that design, and it's actually quite a whole field talking about elevators. That's what they're looking at is, you know, how fast can we go up, how fast do we want to go up, and so on and so forth. All right. Okay, moving along to efficiency. So as discussed, so I'll just get a bit of a bar across here. So as discussed with the bouncing ball, you only see 100% transfer of energy in the physics world. All right, we'd never see this in the real world because we lose energy to sound, or it could be heat, etc. So there is undesirable forms of energy out there that siphon off that total amount of energy. So law of conservation of energy says we can't create it or destroy it, but it gets transferred into those undesirables, such as sound and heat. When you look around stores selling common household items, they talk about efficiency, and it's a huge thing right now when we're talking about energy conservation. So what is mechanical efficiency? So mechanical efficiency is what we're looking at, and it's the percentage of useful energy from the total energy in. So what percentage we put in so much energy, what percent of that was actually doing what we want to do? Okay. So the example here, what is the efficiency of a 100 kilogram person to climb the stairs 20 meters? So it was like the previous example, if they really used 25,000 joules of energy. All right. So when you do the calculations, mechanical efficiency, here's your formula, is equal to, it's your theoretical. So theoretically, how much was needed? Divided by actual, multiplied by 100 to get it into a percentage. So theoretically, if you flip back in your note, it took this individual 19,620 joules of energy to climb the stairs. But in reality, when you climb stairs, what's happening? Well, you start to perspire, start to sweat, start grunting as you get higher and higher. It's a lot of work. So your body starts creating, you know, undesirable side effects or energies that's taking up from that pool. So 25,000 joules is what was actually input by you. So when you do that, 19,620 divided by the 25,000, we get 78%. So the person is only 78% efficient. All right, that means that using that chemical energy, muscle energy, only 78% is going to actually climbing up the stairs. The rest of it is going to undesirable energies. So here's another formula for your formula sheet that you want to include. All right, and I got one last example then. And this is a hot topic right now. I'm talking about light bulbs. So with the light bulb, a light bulb is 10% efficient. So that's old um, the old light bulbs, the incandescent light bulbs. All right. So A part, how much light energy is actually provided to a 100-watt bulb in 60 seconds? All right. So we know mechanical energy is equal to theo over actual times 100. So we know it's 10% efficient, and we have a 100-watt supply. So that is our theoretical. Sorry, the 100 watts, that's your theoretical. Oh, we have to do calculation. We need energy. That's the problem here. So off to the side, power is energy over time, 100 watts. Looking for the energy, 60 seconds. So that means we have equal to 6,000 joules of energy. All right, so I had to convert that power calculation, bring it over here. So that is our theoretical, what we think is actually happening. Or actual, I should say. So theoretical over 6,000 times 100. So now we have to do opposite operations here. First thing is we'll divide by 100. So that gets me 0.1 equals theo over 6,000 multiplied by 6,000. Oops, 6,000. And we get theoretical is equal to only 0.1 of that, which turns out to be 600 joules. Therefore, only 600 joules out of 6,000 joules is light. So those old light bulbs, the ones that really heated up, most of that energy was going to heat. So only 600 joules of that 6,000 was actually becoming light. So what would effective light power be from the light bulb? Well, so in B part, power is your energy over delta T. So your power, we're only using 600 joules of energy in the 60 seconds. So that cancels down and gives us 10 watts. Therefore, 10 watts of light is the actual. Okay? It is actual. So that means that when you were putting in 100-watt light bulbs in the old days, then you were only really getting 10 watts of light. It just meant that a 100-watt light provided what you'd hopefully get. Now, the new light bulbs, the CFLs and the LEDs, are hugely more efficient in the fold of 50+%, which means that more energy is being converted to light. So that's why these new light bulbs are now only, the CFLs, when you go to buy them, they're 13 watts, they're 8 watts, because they only have to create 10 watts of light. And if they're highly efficient, a 13-watt light bulb is only maybe losing 3 watts due to heat or other undesirable effects. So that's why there's a huge push to go onto the CFLs, because instead of losing 90% of the energy, you're actually using 90% of the energy for what you want. So it's kind of neat that way. Anyway, any questions, let me know, and I'll give you a hand in class. Good luck.